So from the first fit I did, we can see that if I let it run out in time, I will indeed reach a peak, and then it will come back down, right? Because the disease will go through the population, and then eventually it'll lessen the number of susceptible people, so it'll have to come back down. And we can see, I estimate here that the peak occurs at this point, 96.6, and then 0.3965. So like I said, day 0 was on February 15th. So the peak is projected to occur May 22nd, for at least what I have fit. Don't take this to be definitely true, but it should be pretty close. May 22nd is a projected peak, with approximately almost 4 million people having been infected by the peak. I'm measuring in tens of millions, so just take whatever numbers you see and multiply by 10 to the 7th. Okay, so we get this curve, the curve we've been seeing. But what we noticed in the previous slide was that, right, my original fit is overestimating what's actually happening, right? I fit my data up until this last red data point, and then I wanted to see what would keep happening. And what's happening is there's less infected people than what I projected there to be, which is a good thing. And so what I decided to do is refit to this new amount of data I have. So I can refit it and get a new fit. And so now what used to be blue data points now became red, and what used to be blue over here can become black. And so again, I get a nice fit. But again, we're not really interested in what's happening right now. What we want to know is, when is this going to peak? When can we all get back out of our houses? So again, I'm going to run the infected population out through time, and we get another curve. And we can see now the peak is occurring at a different point. It's occurring at about day 80, with only about 1.4 million people getting sick. Now we can see the peak occurs May 6th instead of May 22nd, I believe is what I had the first one being. And so this is what basically this is what they're doing every day. They're recalculating this peak, and that's why we're getting so much uncertainty of when this is going to end, right? I think I compared them side by side, right? Within 4 days, I moved the peak from here down to here, right? But what could happen is, in the next 3 days, we could have a surge of infected people, and then the peak could, you would need to refit it again, and then we would have that the peak could move even higher. It's kind of like when they're trying to predict hurricanes, and the cone of uncertainty, and each day they've moved the hurricane. I used to live in Florida, so I understand this. But right, each day the hurricane moves somewhere new, because each day you're collecting more and more data, which is why these peaks and the day at which it's going to peak keeps changing. Because as we get more data, we're able to predict even better. That's why there is so much uncertainty with all.
There's also other factors that could be taking place too. Like the policies that the governor has passed with more strict social distancing, and that's why the blue dots were a little lower than the projected ones.
And so speaking of that, we've all been quarantining, and we all want to know, well, hopefully it's helping. Well, if we look at the equations, and if we take out that quarantining part, so we let those two alpha terms go to 0, right? We ignore quarantining. This is what the model predicts would happen. Basically, the entire population will become infected, and then we would slowly come down. You can barely even see, if I didn't make this bold, you actually couldn't see the fact that with quarantining, right, there's basically nobody there. Basically, the entire population would get sick without quarantining. Okay, so the last little bit is looking at mathematically why this spreads. So less pictures and more equations. So if you like equations, here's the part of the talk for you. So what we're going to be interested in is looking at how the this rate of infection at t equals 0. So this was our equation for the infected population. Just to remind us, we want to look at it at time t equals 0. Each of those terms has an I in it, so I'm just going to factor out the I. And then at t equals 0, we have the initial infected population, or for I, we can replace that, and we have the initial susceptible population, which I'm just going to denote I sub 0 and S sub 0. Okay. So we have two options. Either this value can be greater than 0, or it can be less than 0. And the infected population is always going to be something positive. And so I'm just going to focus on everything that's inside the parentheses, and I'm going to solve for S sub naught. Okay. So we have two options. Either S sub naught is greater than this fraction, gamma plus alpha 2 plus delta divided by beta, or S sub naught is less than this fraction. If S sub naught is less than this fraction, so this piece over here, what's going to happen is that the rate of the infectious population is going to be the rate of change of the infecteds is going to be less than or equal to 0. It will make this piece be negative, and that's going to cause the population to die out. Whereas on this side, this will cause the rate of change of the infected population to be greater than 0, and so the infection will spread. So it's really dependent on what this value is, whether it's greater than or less than our initial population. Okay. So I'm going to call this fraction rho just so that we can look at it. So we're interested in rho, that's the value, and whether or not it's greater than or less than our initial population. Okay, and this is just called the relative removal rate. So plugging in the values that I got for for gamma, alpha 2, delta, and beta for the second time I fit, I get a value of approximately 8.8276. And then I compared it to my S naught value. S naught is 32.72. Remember, I'm measuring in tens of millions, so that's not how many people I have, but my units, right, are larger. But we compared this number, the 32.72 with the 8.8276, and that is larger, right? And so we said S naught is greater than rho, then we should have an epidemic. Now, epidemic, mathematically, math bio speaking, just means that your infected population increases over the initial amount for some time t. So, right, the world thinks epidemic, right, as in like everyone gets it mathematically, math bio speaking, epidemic just means you will have an increase in the infected. So we can show why that happened for this case, because our S naught is greater than rho. And then, so that gets talked about a lot, but the thing that really gets talked about with epidemiology models is the basic reproduction number, R naught. And this is what Dr. Melara was talking about when he first introduced epidemic models, when he had the one infected person, and then he said, well, no one could get sick, or maybe just Dr. Kennedy got sick, or Dr. Kennedy and Dr. Taylor got sick, right? Or 4 people wound up getting sick. And so that number, right, is the number of people, this number R naught is the approximate number of people that each infected person will then infect, right? The secondary infections that one person will cause. And the way you find that is you take your initial susceptibles and you divide it by row. And so I did that for our values, and you get a number about 3.7. What this means is that for every infected person, if they were allowed to be just in the susceptible population, almost 4 people would get sick every time they were in the susceptible population. Anytime R naught is greater than 1, right, you're going to have epidemic the epidemic definition that I gave previously, right, which makes sense. Anything over 1 means that there's always going to be at least 1 person getting sick every time. Anything less than 1, you're having less than 1 person get sick every time, so it should eventually die out. And then, we have just a couple resources you can.
So these are just some resources that were used for this presentation and are also highly cited or are keeping track of the spread of this disease. The one on the left is a very common one that you hear on the news. It's at the University of Washington. The one on the right, I just became aware of this one within the last week, and it's at Los Alamos National Lab. They could have been running from the get-go, but I just became aware of them this past week. And then we have a couple more. So then another one that probably gets the most visibility is the one from Johns Hopkins. So we've included their URLs there. And this last one, Dr.
Yeah,
Barnaby?
so this Worldometer one is the one where I was able to get all the data. And they have daily, they post the number of infected and the number deaths, and they've kept it, they have the graph posted. So it's not just like this every day where they just post this, but they've logged it. So you can follow kind of the curve in real time.
And on that note, thank you on behalf of the two of us and for joining us on this session, and we'll take any questions at this point.